How long is the coastline of Britain? It sounds like a question with an answer. The kind of thing you would look up in an atlas or on a government website and find a single number, clean and settled. And you can find numbers. The Ordnance Survey will give you one. The CIA World Factbook will give you a different one. So does the United Nations. So does Wikipedia. They all disagree, sometimes by thousands of kilometers. And the reason they disagree is not that anyone made a mistake. It is not that someone's measuring tape was off, or that one surveyor was lazier than another. The reason is that the coastline of Britain does not have a length, not approximately, not within some reasonable margin of error. The concept of a fixed measurable length does not apply to a coastline. It never did. It cannot. And the fact that you were never told this, the fact that you went through an entire education system in which the shapes of the natural world were presented to you as though they could be captured by smooth lines and gentle curves, and the clean geometry of Euclid should make you uncomfortable. Because the people who discovered why coastlines cannot be measured also discovered something far more disturbing. They discovered that almost nothing in the physical world has a smooth surface or a definite length or an integer number of dimensions. They discovered that the geometry taught in every school in every country on Earth, the geometry that has dominated human thinking about the shape of reality for over 2,000 years, does not accurately describe a single natural object. Not a cloud, not a mountain, not a tree, not a river, not a snowflake, not the surface of your own lungs. And the mathematicians who first saw the real shape of things, who built the tools to describe what nature actually looks like, were not celebrated for it. They were called monsters. Their work was called a plague. One of them died in a mental institution. One of them swallowed poison rather than be sent to a concentration camp. One of them had his face destroyed by a bullet at age 21 and wore a leather mask for the rest of his life. One of them watched his life's work burn when the Nazis leveled Warsaw. Their mathematics, which the establishment spent a century calling pathological and useless, turned out to be the most accurate description of the physical world ever devised. And nobody told you about it. Not really. Not what it actually means. This is the story of fractal geometry. And the reason you have never heard it told this way is that its implications are the kind of thing most people, including most scientists, would rather not follow all the way to the end. It begins with a pacifist trying to prevent war. Lewis Fry Richardson was born in 1881 in Newcastle upon Tyne into an English Quaker family. He became a meteorologist, a physicist, a mathematician, and a peace researcher. His life's mission was to find mathematical laws that could predict and prevent armed conflict. He spent decades compiling quantitative data on every deadly quarrel between nations since 1820, classifying wars by their magnitude, the way geologists classify earthquakes by theirs. He wanted to know if border length between countries predicted their probability of going to war. It was a reasonable hypothesis. Longer shared borders mean more opportunity for friction, more disputed territory, more flashpoints. But to test it, Richardson needed accurate border measurements, and when he started collecting them, something did not make sense. Portugal reported its border with Spain as 987 kilometers. Spain reported the exact same border as 214 kilometers, a discrepancy of 23% for the same line on the same map between two countries that presumably know where their shared border is. The explanation was almost embarrassingly simple. The two countries had used different measurement scales. Portugal's cartographers measured with longer rulers, which cut across small bends and ignored minor irregularities. Spain used shorter rulers, which followed more of the border's twists and turns and therefore traced a longer path. The shorter the ruler, the longer the result. Richardson, being Richardson, did not shrug and pick an average. He investigated systematically. He measured coastlines and borders at progressively smaller scales to see if the measured length converged to some stable value. It did not. It never does. For any coastline, anywhere. Use a 100-kilometer ruler to measure Britain's coast and you get roughly 2,800 kilometers. That seems reasonable. Use a 50-kilometer ruler and you get approximately 3,400 kilometers. That is 600 additional kilometers of coastline that appeared out of nowhere simply because you measured more carefully. You did not add any land. You did not change the island. You just looked closer, and the number got bigger. Use a 10-kilometer ruler, and the length jumps again. Use a 1-kilometer ruler, and it jumps again. Use a 1-meter ruler, and it jumps again. There is no scale at which the measurement settles down and delivers a final answer. The closer you look, the longer it gets, because at every scale there are new bays and inlets and promontories and tide pools and individual rocks with their own bumpy outlines. The measurement does not converge. It trends toward infinity. Think about what that means. You live on an island, or near a coast, or you have seen a coast on a map, and you assumed it had a length. It does not. The number written in the atlas is a convention, an agreement to measure at a particular scale, and stop there. It is not a property of the coast itself. The coastline has no length the way your kitchen table has a length. If you measured your table with smaller and smaller rulers, the number would converge to one value, because the table is smooth at the scale of millimeters. The coast is not smooth at any scale, down to the scale of individual grains of sand. It keeps getting rougher, and the measurement keeps growing. Richardson found a mathematical law governing this growth. The measured length L relates to the ruler size S by a power law. L equals F times S raised to the power 1 minus D, where F is a constant and D is a number that depends on the particular coastline. He wrote this formula down. He did not know what D meant. He had no theoretical framework for it, no name for the phenomenon he was observing. He was a peace researcher, not a geometer. He published his findings as an appendix to his work on deadly quarrels in the General Systems Yearbook in 1961, 8 years after his death. Nobody read it. Nobody cited it. Mandelbrot later wrote, on page 636 of his 1967 paper, that Richardson's formula had unfortunately attracted no attention. Richardson's own life was full of the kind of irony that seems almost designed to hurt. During the First World War, as a Quaker and a conscientious objector, he refused to fight, but served with the Friends Ambulance Unit in France, saving lives in the same trenches where men were trying to kill each other. During that war, he attempted the first ever computational weather forecast, working out by hand a prediction for atmospheric conditions on May 20th, 1910. The forecast failed spectacularly, predicting a pressure change of 145 hectopascals when the actual pressure was essentially stable. But the method was sound. Richardson estimated that performing a real-time weather forecast would require 64,000 human computers working simultaneously with slide rules, essentially describing electronic computers several decades before they existed. Every weather forecast you have ever seen, every hurricane track prediction, every climate model descends from Richardson's failed calculation in a trench. He also patented acoustic echolocation for iceberg detection. After the Titanic sank in 1912, 6 years before sonar was formally developed, he saw the self-similar, recursive structure of nature in everything he studied, from turbulence to war patterns to coastlines. He even wrote a verse about it that physicists still quote: "Big whirls have little whirls that feed on their velocity, and little whirls have lesser whirls, and so on to viscosity." He described fractals before the word existed, died in 1953, and his most important discovery was published as a footnote to his peace research, where it sat, unread, for 6 years. And here is where a problem about coastlines becomes a problem about everything. Because the unmeasurable roughness Richardson found does not stop at shorelines. The same behavior, the same refusal to converge, the same increasing complexity at every smaller scale appears in the branching patterns of rivers, in the ridgelines of mountains, in the edges of clouds, in the forking paths of lightning, in the branching of trees, in the fractal network of blood vessels in your own retina, and in the trajectories of subatomic particles, as if something at the very bottom of reality insists on this shape, as if the universe has a preferred geometry, and it is not any geometry you were taught in school, as if nature has been whispering the same pattern at every scale, from the quantum to the cosmic, and we spent 2,000 years with our fingers in our ears chanting about circles and spheres and smooth, differentiable curves. It took a refugee to finally hear it. Benoit Mandelbrot was born in Warsaw on November 20th, 1924, into a Lithuanian Jewish family. His father was a clothing merchant. His mother was a dental surgeon. The family valued learning above almost everything, and young Benoit, kept home from school by a mother who feared epidemics, was tutored informally by relatives. He later said he spent most of his time playing chess, reading maps, and learning to open his eyes to everything around him. When he was 11, in 1936, the family fled Warsaw for Paris, driven by the gathering darkness of anti-Semitism in Poland. His uncle, Solomon Mandelbrot, a distinguished mathematician who held a chair at the Collège de France and was a founding member of the Bourbaki group, had already established himself in France. Mandelbrot later wrote that the fact that his parents, as economic and political refugees, joined Solomon in France saved their lives. When the war came and the Germans occupied northern France, the family fled south to Toul in central France. By 1943, even Toul had become dangerous. The family split apart. Benoit and his brother Leon made their way to Lyon, where they lived under assumed identities, moving frequently, always aware that a single denunciation could mean death. It happened to people they knew. A close friend from Paris, a physician named Zina Morhange, was turned in by another doctor who simply wanted to eliminate a professional rival. She was sent to her death. The Mandelbrots survived. Benoit later wrote that he did not know why, that it could have gone either way. He worked as an apprentice toolmaker for the railroad and cared for horses. He attended classes when he could, sporadically, at whatever school would take him. He described himself as essentially self-taught. That disrupted, improvised education turned out to be the most important accident of his life. Because Mandelbrot free from the rigid formalism that dominated French mathematical training, developed a fiercely visual, intuitive, geometric way of thinking. At the Lycée du Parc in Lyon, he discovered he could reformulate algebraic problems as geometric ones, watching shapes move fluidly in his mind, while his classmates saw only strings of symbols. He later said that everybody in mathematics had given up for 100 or 200 years on the idea that you could discover new things just by looking at pictures. He never gave up on it. It was the only way his brain worked. After the war, Mandelbrot aced every exam France could throw at him. He placed first in the entering class at the École Normale Supérieure, the most prestigious gateway to French academic mathematics. He lasted 1 day. The institution was dominated by the Bourbaki movement, a collective of mathematicians who championed an abstract, algebraic, rigorously anti-visual approach to their subject. Their books contained almost no illustrations. They viewed geometric intuition as primitive, even dangerous. At a conference in 1959, Bourbaki member Jean Dieudonné reportedly declared, "Down with Euclid, death to triangles." Mandelbrot's own uncle Scholem was a founding Bourbakist. The nephew's entire career would become an open rebellion against everything the uncle's movement represented. Mandelbrot transferred to the École Polytechnique, where he studied under Gaston Julia and Paul Lévy. He earned a master's degree in aeronautics at Caltech in 1949, a PhD from the University of Paris in 1952. He spent time at Princeton's Institute for Advanced Study, sponsored by John von Neumann, one of the most powerful minds of the 20th century. And none of it, not the brilliant exam scores, or the famous sponsors, or the multiple degrees, led to a permanent academic position. The mathematical world had no category for someone who thought in pictures and refused to specialize. In 1958, Mandelbrot visited IBM's Thomas J. Watson Research Center in Yorktown Heights, New York, for what was supposed to be a summer project. He stayed for 35 years. He later explained it simply. He was in an industrial laboratory because academia found him unsuitable. IBM gave him something no university department could have offered: freedom to roam across disciplines without justification, access to the most powerful computers in the world, and no pressure to produce papers in any one field. He said he touched on far more topics than anybody would have found reasonable, that people constantly told him to settle down, to stay in one area, but that he was compelled to keep moving. At IBM, that restlessness was a feature, not a failing, and the roaming led him somewhere extraordinary, because the same pattern kept showing up in everything he looked at. He started with noise in telephone transmission lines for IBM. The errors were not evenly distributed. They clustered. Zoom into a period of heavy errors, and you found clusters within clusters, bursts within bursts, the same statistical structure, repeating at every time scale. Then he looked at cotton prices on the New York Mercantile Exchange, a century's worth of data. The fluctuations were not Gaussian. They were self-similar across timescales. A graph of daily price changes looked statistically identical to a graph of monthly changes, which looked identical to a graph of yearly changes. The same roughness at every scale. Then he looked at the flooding patterns of the Nile, using records that went back over 1,000 years. Same pattern. Hydrology, economics, telecommunications. 3 completely different fields, 3 completely different physical systems, and the same statistical signature underneath all of them. This was not coincidence. Something structural was happening, something about the way nature organizes complexity, and it was connected to those monstrous curves the mathematicians had been trying to kill for a century. In 1967, he published 3 pages in the journal Science that changed the trajectory of mathematics. The paper was titled, "How Long is the Coast of Britain? Statistical Self-Similarity and Fractional Dimension." In it, he took Richardson's forgotten data, the power law measurements that had been sitting unread in that Peace Research yearbook for 6 years, and connected them to an old mathematical concept that almost nobody was thinking about. The concept was the Hausdorff dimension, and what it said about coastlines was that they do not live in one dimension like a line or 2 dimensions like a surface. The coast of Britain occupies a dimension of approximately 1.25, more than a line, less than a plane, a fractional number, a dimension that is not supposed to exist in the geometry you learned in school. Mandelbrot wrote on the first page of that paper that Richardson's empirical formula had unfortunately attracted no attention. He was correcting a decades-long injustice, and he was opening a door that the mathematical establishment had spent half a century trying to lock, because the man who created the Hausdorff dimension, the tool that finally gave mathematical meaning to coastline roughness, had been dead for 25 years by the time Mandelbrot used it. And the way he died is one of the darkest stories in the history of science. Felix Hausdorff was born in 1868 in Breslau, which is now Wrocław, Poland, into a prosperous Jewish merchant family. He was a polymath in the fullest sense before becoming one of the foremost mathematicians in Europe. He published poetry, philosophical essays on Nietzsche, and a satirical play under the pen name Paul Mongret that was performed over 300 times in 31 cities across Germany. He was witty, cultured, and deeply engaged with the arts. His philosophical work on the concept of time and recurrence led him to George Cantor's revolutionary set theory, and from there into topology and measure theory, the mathematical study of how to assign size and dimension to abstract objects. In 1918, in a paper published in the journal Mathematicians titled Dimension and Äußeres Maß, Hausdorff defined a new way to extend the concept of dimension beyond whole numbers. His approach used measures, a generalization of the idea of length and area, to capture how thoroughly a shape fills the space around it. A smooth curve gets dimension 1. A filled-in square gets dimension 2. But an irregular, jagged, self-similar shape like a coastline gets something in between. Britain's coast at approximately 1.25, meaning it is 25% more space-filling than a simple line twisting and folding through the plain without ever actually covering it. Norway's coast, slashed by deep fjords, at approximately 1.52, nearly halfway to being a surface. South Africa's coast, relatively gentle, at approximately 1.02, barely more than a line. The mathematical establishment at the time had no interest in this. The objects that Hausdorff's dimension was designed to measure had already been classified as pathological, monstrous, useless curiosities that served no purpose in describing the real world. This classification had been building for decades. In 1872, Carl Weierstrass exhibited a continuous function that was differentiable nowhere, a curve with no smooth point at any magnification, infinitely jagged everywhere you looked. Charles Hermite, one of the great French mathematicians, reacted with revulsion. In a letter dated May 20th, 1893, he wrote that he turned away with fear and horror from the lamentable plague of continuous functions that do not have derivatives. Those are his actual words: fear, horror, plague, about a mathematical object. Henri Poincaré, arguably the most brilliant mathematician of the era, was even harsher. He described these shapes as monsters. He called the growing collection of them a teratological museum, a gallery of freaks. He wrote that in earlier times mathematicians invented new functions to serve practical ends, and now they were invented solely to expose the defects in the reasoning of their fathers. This was not idle commentary. It was policy. The message from the top of the profession was clear. These objects were embarrassments. They were to be studied only as cautionary examples of what happens when mathematical logic goes too far. They were certainly not descriptions of anything real. And Georg Cantor, who started the whole thing, who cracked open the door through which all the monsters would eventually pour, was systematically destroyed for it. Born in St. Petersburg in 1845, into a family of merchants and musicians, Cantor showed exceptional mathematical talent from childhood. His father, a deeply religious man, encouraged Georg's gifts while warning him that the path would be difficult. He could not have known how prophetic that warning would be. Cantor studied at the University of Berlin under Weierstrass, Kummer, and Kronecker, the most formidable trio of mathematicians in Germany. He earned his doctorate in 1867 and took a position at the University of Halle, where he would remain for his entire career, not by choice, but because every attempt to move to a more prestigious institution was blocked. In the late 1870s, Cantor began publishing the work that would simultaneously create modern mathematics and destroy his mental health. He proved that infinity comes in different sizes. He showed that the set of real numbers is uncountably infinite, larger in a precise mathematical sense than the infinite set of whole numbers. This was not a metaphor. It was a theorem, and it implied that there are degrees of infinity, an infinite hierarchy of infinities, each one larger than the last. The philosophical implications were staggering, and much of the mathematical establishment recoiled. Along the way, in 1883, he described a set that would become one of the first recognized fractal objects. Start with the line segment from 0 to 1. Remove the middle third. Take each remaining piece and remove its middle third. Repeat forever. What remains is the Cantor set, an uncountably infinite collection of points with zero total length. It has as many points as the entire real number line, yet it takes up no space at all. Dust made of infinity. Its fractal dimension is the logarithm of 2 divided by the logarithm of 3, approximately 0.631. Not zero-dimensional like a collection of isolated points, not one-dimensional like a line, something in between, something that should not exist in the tidy world of integer dimensions. His former professor, Leopold Kronecker, reportedly called him a scientific charlatan and a corrupter of youth. Kronecker used his editorial power to delay and obstruct Cantor's publications and ensured that Cantor never received a position at the University of Berlin, the most prestigious mathematics department in Germany. Poincaré called set theory a disease from which future generations would recover. Cantor's first major depressive episode struck in May of 1884. He was hospitalized repeatedly over the next 3 decades. His youngest son, Rudolf, died suddenly in 1899 while Cantor was at the lectern delivering a talk. He was committed to the Halle Nervenklinik for the final time in June of 1917. He spent months writing letters to his wife, begging to be allowed to come home. He died there on January 6, 1918, malnourished during the wartime food shortages, alone. David Hilbert's defense of Cantor's work became one of the most famous lines in mathematics. No one shall expel us from the paradise that Cantor has created. But Cantor never heard it. He was already gone. Helge von Koch, a Swedish mathematician, published a curve in 1904 that made the problem visually undeniable. Start with an equilateral triangle. On the middle third of each side, attach a smaller equilateral triangle. On every new side of the resulting shape, attach a still smaller one. Repeat forever. The Koch snowflake has an area that converges to a finite value, exactly 8/5 of the original triangle's area. You could calculate the area. You could color it in. You could cut it out of paper, if paper were infinitely thin and infinitely divisible. But its perimeter grows by a factor of 4/3 at every iteration and never stops. After the first iteration, the perimeter is 4/3 times the original. After the second, 16/9. After 10 iterations, the perimeter has grown by a factor of roughly 17.8. After 100 iterations, which is still infinitely far from the limit, the perimeter has grown by a factor so large it exceeds the number of atoms in the observable universe. And it keeps growing, a bounded shape with an infinite boundary. You can hold it in your hand. You could never walk around it. Its fractal dimension is the logarithm of 4 divided by the logarithm of 3, approximately 1.262, almost identical to the measured fractal dimension of Britain's coastline. Koch built it as a simple pedagogical example, a concrete geometric version of Weierstrass's analytical monster. What he actually produced, without knowing it, was a miniature of every irregular shoreline on the planet. The monster was a portrait of nature, and nobody recognized it for another 60 years. And Hausdorff, whose mathematical dimension finally gave these objects their proper measurement, was killed not by mathematics, but by history. Under the Nazi regime, his work was classified as Jewish mathematics. He was forced to retire from the University of Bonn in 1935. In 1939, he wrote to colleagues in the United States requesting help in emigrating. The appeals were unsuccessful. By January of 1942, wearing the mandatory yellow star, he and his wife Charlotte received orders for deportation to the Endenich internment camp, a converted monastery used as a way station to the camps in the east. On the night of January 25, 1942, Felix Hausdorff, his wife Charlotte, and her sister Edith Pappenheim took lethal doses of the barbiturate veronal. In a farewell letter to his friend, the lawyer Hans Wallstein, Hausdorff wrote that what had been done against the Jews in recent months aroused well-founded anxiety that they would not be allowed to experience a bearable situation. He asked forgiveness for causing trouble beyond death. He was 73 years old. The letter was believed lost for decades. In 2012, Bonn University archivist Thomas Becker found it during a routine inspection, sitting on a stack of empty leaflets. The man who invented the tool to measure the true roughness of the world chose death over what the world had become. His mathematics, ignored for half a century, eventually proved to be the key to describing every jagged edge in nature, and the objects it measured, the monsters the establishment had tried to kill, turned out to be nature itself. By the mid-1970s, Mandelbrot had spent nearly 2 decades at IBM, following the thread that connected all of these stories: cotton prices and the flooding patterns of the Nile, and turbulence in transmission lines, and Richardson's coastlines, and the clustering of galaxies, and the distribution of word frequencies in natural language. He saw the same roughness everywhere, the same statistical self-similarity across scales, the same refusal to smooth out. He later wrote that nearly all common patterns in nature are rough, and that for centuries, the very idea of measuring roughness was an idle dream. He described this as one of the dreams to which he had devoted his entire scientific life. In 1975, looking through his son's Latin dictionary, he found the word fractus, meaning broken, fragmented, irregular. He coined the word fractal. He later said that after inventing the term, he sorted through his own research over a period of many years and realized he had been doing almost nothing else his whole life. Everything he had studied, from the errors in telephone lines to the flooding of rivers to the shape of coastlines, was the same phenomenon: roughness, self-similarity, fractional dimension. He just had not had a name for it. In 1982, he published The Fractal Geometry of Nature, which began with the single most devastating sentence ever written about Euclidean geometry. Clouds are not spheres, mountains are not cones, coastlines are not circles, and bark is not smooth. Nor does lightning travel in a straight line. But the centerpiece of Mandelbrot's work was not a sentence. It was an object, and that object should not be possible. The equation is 5 symbols long. Take a complex number c. Start with z equals 0. Square z and add c. Take the result and do it again and again. If the sequence of numbers you produce stays bounded, if it never grows past a magnitude of 2 and escapes to infinity, then c belongs to the set. If the sequence blows up, it does not. That is the entire rule. Squaring and adding. A child could perform the operation. And from this rule emerges the Mandelbrot set, a shape whose boundary contains structure at every magnification, without limit. Zoom in on the boundary, and you find spirals, and seahorse tails, and lightning bolt tendrils, and miniature distorted copies of the entire set, connected to the main body by filaments so thin they are invisible at lower magnifications. Zoom into those miniature copies, and the same structure recurs. Zoom into those copies, and it happens again. There is no bottom. There is no resolution at which the pattern finally smooths out. You can zoom by factors of 10 to the power of 200, far beyond the scale at which individual atoms would be visible if this were a physical object, and still find new structure, new spirals, new copies, new filaments connecting structures you could not have predicted from any amount of study at the previous magnification. The depth is not just large, it is infinite, mathematically, provably infinite. Every person who has sat in front of a computer watching a Mandelbrot zoom knows the uncanny feeling. You are watching 5 symbols generate more visual complexity than everything every human being has ever seen in the natural world. And you know, mathematically, that what you are seeing is an infinitesimally small fraction of what the set contains. You could zoom for the remaining life of the universe and never exhaust it. The entire artistic output of human civilization contains less detail than one sliver of this boundary. The total area of the set has been estimated computationally at approximately 1.5066, a finite number, but its boundary has a Hausdorff dimension of exactly 2. In 1991, Mitsuhiro Shishikura proved this. The paper was published in the Annals of Mathematics in 1998. What this means is that the boundary, which is topologically a curve, a one-dimensional object, is so infinitely contorted that it fills the plane as completely as a two-dimensional region, a line that has become a surface, generated by squaring and adding. Arthur C. Clarke described it as one of the most astonishing discoveries in the entire history of mathematics, and asked who could have dreamed that such an incredibly simple equation could generate images of literally infinite complexity. The set was first computed in 1978 by Robert Brooks and Peter Matelsky, who published a crude asterisk printout in conference proceedings. It looked like a smudge. On March 1st, 1980, Mandelbrot generated his own images at IBM using the company's powerful mainframes, and the results were unlike anything mathematics had ever produced. The shapes looked organic. They looked alien. They looked alive. And the Mandelbrot set is not merely an image. It is a map. Every point in the complex plane corresponds to a Julia set, the particular fractal shape generated by iterating z squared plus c to that specific value of c. If c is inside the Mandelbrot set, the corresponding Julia set is connected, one unbroken fractal form. If c is outside the set, the Julia set shatters into an infinite cloud of disconnected points, what mathematicians call Cantor dust. The Mandelbrot set is an atlas of every possible Julia set, an infinite encyclopedia indexed by a 5-symbol rule. Gaston Julia, the man whose name those fractured sets carry, lived a life of almost unbearable irony. Born poor in 1893 in French colonial Algeria, Julia was brilliant enough to place first in entrance exams at both the École Normale Supérieure and the École Polytechnique. On January 25, 1915, at the age of 21, fighting at the Chemin des Dames Ridge in his very first engagement under enemy fire, a German bullet struck him in the center of his face. The military report says he could no longer speak, but wrote on a slip of paper that he would not be evacuated. He stayed at his post until the attack was repelled. He lost his nose. He endured multiple operations over the following years, and for the remaining 63 years of his life, he wore a leather strap across the center of his face. Between operations, still recovering in hospital at the age of 25, he wrote a 199-page masterwork on the iteration of rational functions. It won the Grand Prix of the Académie des Sciences and was celebrated as a landmark. And then, within a few years, it was almost completely forgotten. The mathematics it described, the iteration of simple functions in the complex plane, was too abstract to visualize and too alien to connect to the physical world. Julia's work gathered dust for over half a century. It took Mandelbrot, who had studied under Julia at the École Polytechnique in the 1940s, and the computers at IBM to reveal what was hiding inside the equations. The infinite beauty Julia had described with symbols, the shapes he could never see, became visible for the first time in the late 1970s. Julia died in March of 1978, just months before the images appeared. He never saw them. The most visually extraordinary objects in the history of mathematics were first described by a man who lived behind a mask, and the technology to see them arrived just after he was gone. If the universe has a sense of irony, this is its cruelest expression. And here is where the story makes a turn that most tellings miss entirely. Because everything you have heard so far, the coastline paradox, the monster curves, the Mandelbrot set's infinite depth, you could dismiss all of it as pure mathematics, beautiful but abstract, disconnected from the physical world you actually inhabit. Except it is not disconnected. The mathematics of fractals is not confined to theoretical objects and idealized coastlines. It is in your body at this moment. It is what your body is made of. Your lungs are fractal. The bronchial tree, the branching network of airways that delivers oxygen to your blood, divides approximately 23 times, starting from the trachea and ending at roughly 300 million alveoli. Through this fractal branching, approximately 70 square meters of gas exchange surface area, about the size of a singles tennis court, is packed into a chest cavity, no larger than a small suitcase. The three-dimensional fractal dimension of this network is approximately 2.7, nearly space-filling. Your body solved the packing problem that would stump most engineers by using fractal geometry. Your blood vessel network is similarly fractal. It extends approximately 100,000 kilometers through progressively smaller self-similar branches, enough to wrap around the Earth 2.5 times, reaching every single cell. The fractal dimension of healthy retinal blood vessels is approximately 1.7. And here is where it stops being merely interesting and starts being medically important. In cancer patients, tumor blood vessels show a fractal dimension of approximately 1.89, measurably more chaotic, more irregular, more space-filling than normal vasculature. That quantifiable difference between 1.7 and 1.89 is now used in medical imaging to detect disease before a patient has symptoms. The same mathematical framework that was called pathological for 100 years turned out to measure the literal pathology in your blood. Your heartbeat is fractal. A healthy heart does not beat like a metronome. It shows variation on every time scale, a fractal signature of complexity. When the fractal dimension of heart rate variability drops, when the rhythm becomes either too regular or too chaotically irregular, it predicts cardiac events. The geometry the establishment rejected is the geometry that keeps you alive. In 1988, a radio astronomer and ham radio operator named Nathan Cohen attended a conference in Hungary, where Mandelbrot lectured on fractal landscapes. Cohen faced a practical problem. He lived in a Boston apartment building with a strict no antenna policy, and he needed to receive signals across multiple frequency bands. Standard antennas are tuned to one frequency and must be a specific size, typically a fraction of the wavelength. Cohen had an idea. He fashioned a fractal antenna from aluminum foil, glue, and construction paper, roughly 6 inches on a side, and attached it to his balcony railing on the 27th floor. It worked. It picked up multiple frequency bands in a fraction of the space a conventional antenna would need, because the fractal shape packed multiple resonant lengths into the same compact area. When his landlord discovered it and cut it down, Cohen found what he later described as the sad remains in the snow. He went on to found fractal antenna systems, file patents, and develop the technology that now lives inside virtually every smartphone, every laptop, every Wi-Fi router, every wireless device on Earth. The monstrous mathematics is in your pocket right now. In 1980, a Boeing engineer named Loren Carpenter saw Mandelbrot's fractal images and realized fractal algorithms could generate photorealistic computer landscapes. He created a 2-minute animated film called Vol Libre and presented it at the SIGGRAPH Computer Graphics Conference on July 14, 1980. The audience gave a standing ovation. Ed Catmull and Alvy Ray Smith of Lucasfilm offered him a job immediately. His fractal landscape technique produced the Genesis effect sequence in Star Trek II, The Wrath of Khan, in 1982, the first entirely computer-generated sequence in a feature film. The Lucasfilm graphics division was sold to Steve Jobs in 1986 for $5 million and became Pixar Animation Studios. Carpenter served as its co-founder and chief scientist. Every computer-generated landscape, every digital forest, every simulated cloud, every procedurally generated terrain in every film and video game you have ever seen descends from the geometry the establishment called monstrous. In 1990, physicist Richard Taylor at the University of Oregon published a paper in the journal Nature, volume 390, page 422, demonstrating that Jackson Pollock's drip paintings are fractal. Not as a metaphor, not as an artistic interpretation, quantifiably, measurably fractal, analyzable with the same mathematical tools used on coastlines and cloud boundaries. Taylor measured the fractal dimension of Pollock's canvases across his career and found a clear trajectory. In his earliest drip experiments, around 1943, the fractal dimension was approximately 1.0, barely more complex than a random line. By 1952, his final and largest drip period, it had risen to approximately 1.7, close to the fractal dimension of many natural phenomena like the branching of blood vessels or the drainage patterns of rivers. His canvases had grown from about 1/3 of a square meter to nearly 10 square meters, and his layering technique had become extraordinarily complex, with paint applied in multiple passes at different speeds and viscosities. Taylor called it fractal expressionism and hypothesized that Pollock's technique was essentially a human body acting as a chaotic pendulum, transferring the fractal dynamics of his own nervous system and musculature onto canvas. In blind authentication tests, fractal analysis correctly distinguished 14 genuine Pollock paintings from 51 non-Pollocks with 100% accuracy. When the Pollock-Krasner Foundation asked Taylor to examine disputed paintings found in a storage locker, his fractal analysis flagged significant deviations from Pollock's characteristic dimensional signature. Materials testing later confirmed the disputed works used pigments manufactured after Pollock's death in 1956. The man's fractal fingerprint was as unique and identifiable as a signature. Pollock once declared that he was nature. His fractal dimensions suggest he was speaking with a literalness that nobody at the time could have appreciated. But here is where the story turns, because fractals do not stop at bodies and antennas and paintings and CGI. They reach into the deepest structure of physical reality, and what they reveal there is something that should have rewritten the foundations of physics decades ago. And it has not, and no one seems to be asking why. The distribution of galaxies in the observable universe is fractal. In 1987, Italian physicist Luciano Pietranero analyzed galaxy survey data and found that at scales below approximately 70 megaparsecs, galaxies cluster in a fractal pattern with a dimension of approximately 2, not uniformly distributed, not randomly scattered. Fractal. Clusters within clusters within clusters. The same statistical pattern at every scale, like a three-dimensional Cantor dust made of galaxies. At larger scales, the distribution appears to transition toward homogeneity, which is what the standard cosmological model requires. But the fractal structure at smaller scales means the visible universe, the part you can actually observe with telescopes, is organized according to the same geometry that organizes your lungs and your blood vessels and the coastline of Britain. The same roughness at every scale, from the quantum to the cosmic. In 1963, MIT meteorologist Edward Lorenz discovered that a simple system of three differential equations describing atmospheric convection produces deterministic chaos. The story of the discovery itself has become legendary. Lorenz was running a weather simulation on a Royal McBee computer and wanted to re-examine a particular sequence. To save time, he restarted the simulation from the middle, typing in the numbers from a printout. The printout had rounded the numbers to 3 decimal places. The computer's internal memory stored them to 6. That tiny difference, the 4th, 5th, and 6th decimal places, caused the simulation to diverge wildly from its original path within a few simulated days. The same equations, the same initial conditions, or so he thought, but the difference between 0.506 and 0.506127 was the difference between a calm Tuesday and a catastrophic storm. The present determines the future, Lorenz wrote in his paper, published in the Journal of the Atmospheric Sciences, Volume 20, Number 2, pages 130 to 141. But the approximate present does not approximately determine the future. The trajectories of Lorenz's system, tracked through phase space, converge toward a structure called the Lorenz attractor, a double-lobed butterfly shape. Its Hausdorff dimension is approximately 2.06, a fractal, not a surface, not a volume, something in between, emerging inevitably from perfectly deterministic equations. Weather is unpredictable not because it is random, but because it is fractal. The atmosphere is a chaotic system whose trajectories lie on a strange attractor of non-integer dimension, and no amount of measurement precision will ever make long-range weather forecasting reliable, because the fractal geometry of the attractor guarantees that infinitesimally close starting points lead to radically different futures. Richardson, who tried to predict the weather from a trench in World War I and failed, would have understood. The system he was trying to forecast was rougher than any instrument could resolve. In 1975, Mitchell Feigenbaum, working alone at the Los Alamos National Laboratory on a handheld HP 65 calculator, discovered something that borders on the uncanny. When dynamical systems transition from orderly behavior to chaos through a process called period doubling, the ratio between successive doubling intervals converges to a universal constant of approximately 4.6692016. Feigenbaum found this number first in the logistic map, a one-line equation that models population growth. He thought it was a quirk of that particular equation. Then he tested it on other equations, the sign map, the Gaussian map, Different equations, different physical interpretations, different curves entirely. The same constant, always 4.6692. He published his results in 1978, and the mathematical community slowly realized what he had found. It was not a property of any particular equation. It was a property of the process of becoming chaotic. Any system that transitions to chaos through period doubling produces the same universal ratio. Dripping faucets, electronic circuits, population growth models, lasers, chemical oscillations, heart arrhythmias, they all produce Feigenbaum's constant. As if the mathematics is not describing different systems at all, but one single underlying process wearing different physical costumes. As if chaos has a structure, and that structure is the same everywhere in the universe. And here is the connection that ties everything together. The bifurcation diagram of the logistic map, which is the simplest equation that generates chaos, corresponds exactly to a cross-section of the Mandelbrot set along the real axis through a change of variables. The buds that sprout from the main cardioid of the Mandelbrot set appear at intervals governed by Feigenbaum's constant. Fractals and chaos are not related subjects that share some mathematical ancestry. They are the same mathematics viewed from different angles. The thing generating the infinite complexity of the Mandelbrot set is the same thing generating weather, turbulence, population cycles, cardiac rhythms, and the behavior of every nonlinear system in the physical universe. And then there are the quantum paths. And this is the part that should disturb you. Richard Feynman's path integral formulation of quantum mechanics, which underpins the most precisely confirmed predictions in the history of science, accurate to 11 decimal places in the case of the electron's magnetic moment, tells you what trajectories quantum particles take through space. The answer is profoundly strange. A quantum particle does not take one path. It takes all paths. Every conceivable trajectory from point A to point B, including paths that loop backward in time, paths that zigzag wildly, paths that make no classical sense at all, contributes to the particle's behavior. Each path is weighted by a complex phase factor, and the sum of all paths produces the observable outcome. And those paths, every single one of them, the ones that contribute to the behavior of every electron and photon and quark in every atom in the universe, are continuous, but nowhere differentiable. They have no smooth points. At every magnification, they are jagged. They are fractal curves with a Hausdorff dimension of exactly 2. Not approximately 2, exactly 2. The same dimension as the boundary of the Mandelbrot set. Think about what that means. The monstrous functions that Charles Hermite turned away from with fear and horror in 1893 are the actual trajectories of every particle in your body right now. The pathological curves that Poincaré put in his Museum of Freaks are the paths traced by every photon of light that has ever entered your eyes. The things the mathematical establishment spent a century trying to suppress are the literal geometry of physical reality at its most fundamental level. The monsters were never pathological. They were never a plague. They were the native language of the universe. And the mathematicians who recoiled from them were recoiling from the actual shape of existence. Laurent Notal's Theory of Scale Relativity, first published in 1993 and expanded in 2011, takes this seriously. Notal models space-time itself as fractal and non-differentiable at quantum scales, and derives the equations of quantum mechanics from purely geometric assumptions about the fractal nature of space. In his framework, quantum behavior is not a mysterious addition to classical physics. It is what you get when you allow space-time to be rough. The weirdness of quantum mechanics, the uncertainty principle, wave-particle duality, the probabilistic nature of measurement, all of it follows naturally from the assumption that space is not smooth. Independently, the causal dynamical triangulation program of Ambjorn, Jerkiewicz, and Lowell, which builds space-time from fundamental simplicial building blocks and lets its geometry emerge dynamically through a kind of quantum gravitational simulation, produces a space-time that is four-dimensional at large scales, but becomes effectively two-dimensional and fractal at the Planck scale. Two different research programs, starting from completely different assumptions, arriving at the same conclusion. The geometry of the universe, at its most fundamental level, is not smooth. It is rough, all the way down to the bottom. If there is a bottom, and if there is no bottom, then reality has the same property as the Mandelbrot set's boundary. Structure at every scale. Forever. No final resolution. No point at which the roughness gives way to smoothness. Jagged all the way down. Stephen Wolfram demonstrated that a cellular automaton called Rule 110, describable in 8 binary digits, is Turing complete, capable of performing any computation that any computer ever built or ever could be built could perform. 8 bits. That is less information than a single letter of the alphabet requires in most computer systems, and it can compute anything. The proof was provided by Wolfram's research assistant, Matthew Koch, and published after a legal dispute that kept it out of the literature for years. The Mandelbrot set generates infinite geometric complexity from 5 symbols. The observable universe generates everything, every star, every planet, every molecule of water, every synapse firing in your brain right now, from a handful of physical constants and equations that fit on a single page. Max Tegmark, a cosmologist at MIT, states the implication directly in his mathematical universe hypothesis. Our reality is not just described by mathematics. It is mathematics, not aspects of it, not the parts we can model. All of it, including you. Eugene Wigner, one of the great physicists of the 20th century, wrote in a famous 1960 essay published in Communications in Pure and Applied Mathematics that the enormous usefulness of mathematics in the natural sciences is something bordering on the mysterious and that there is no rational explanation for it. Why should equations written on paper by human beings successfully predict the behavior of particles billions of light years away? Why should the same mathematics that describes the vibration of a guitar string also describe the quantum states of an electron? Wigner had no answer. Tegmark's answer dissolves the mystery by dissolving the distinction. Mathematics is not a language we invented to describe the world. It is what the world is made of. The reason mathematics works is that you are mathematics. If that is right, then the Mandelbrot set does not merely model nature, it shares nature's ontological status. An equation generating infinite complexity from 5 symbols is not a metaphor for how reality works. It is an instance of the same process, and the infinite depth of the Mandelbrot set's boundary, the fact that you can zoom forever and never reach the end, may be telling you something about the structure of existence that no physical experiment has yet been designed to test. Mandelbrot himself pushed fractal thinking into financial markets, and what he found there was arguably the most consequential application of fractal mathematics in the modern world. In his 2004 book, The Misbehavior of Markets, written with Richard Hudson, he showed that price fluctuations in financial markets are self-similar across timescales. A chart of minute-by-minute price changes in a stock is statistically indistinguishable from a chart of daily changes, which is indistinguishable from monthly changes, which is indistinguishable from yearly changes. The same roughness at every timescale, the same fractal structure he had first noticed in cotton prices back in the 1960s. And crucially, the real data shows fat tails, extreme events that occur far more frequently than the Gaussian bell curve models predict. The standard models used by banks, hedge funds, and regulators assume that market movements follow a normal distribution, where a 5 sigma event, a move of 5 standard deviations, should happen about once every 7,000 years. In fractal markets, events of that magnitude happen every few decades. The 2008 global financial crisis, which standard models computed as having a probability so small it would not occur once in the lifetime of the universe, was not a black swan in Mandelbrot's framework. It was an inevitable feature of a fractal system. The people managing the global economy were using smooth Euclidean statistics to navigate a fractal world, and the mismatch nearly destroyed everything. Mandelbrot had been warning about this since the 1960s. Nobody in finance listened until after the crash, and even then, the Gaussian models were not replaced. He died on October 14, 2010, of pancreatic cancer at a hospice in Cambridge, Massachusetts. He was 85. He had been fighting for recognition since the 1960s. He never stopped. He was never granted a permanent, tenured academic position until 1990, when Yale finally offered one. He was 75 years old. Think about that. The man who discovered the true geometry of reality, whose work now underpins medical imaging and telecommunications and computer graphics and financial risk modeling, spent the most productive decades of his career as an industrial researcher because no university mathematics department would have him. He wrote that for much of his life, there was no place where the things he wanted to investigate were of interest to anyone. When President Sarkozy eulogized him after his death, the French president noted that Mandelbrot's work had been developed entirely outside mainstream research. That was meant as praise. Read it again. It is an indictment of every institution that turned him away. Every person who saw the real geometry of the natural world paid for seeing it. Cantor in the sanatorium, writing letters to his wife, begging to go home, dying of malnutrition during a war that history barely remembers him surviving to see. Hausdorff in his apartment in Bonn with the Veronal and a farewell letter, apologizing for the inconvenience of his death. Julia behind the leather strap that hid the hole where his nose had been, watching his life's greatest work disappear into obscurity for 6 decades. Richardson dead of a cerebral hemorrhage 8 years before his most important discovery was published as an appendix nobody read. Sierpinski, who in 1915 described his famous triangle, a shape with 0 area and a fractal dimension of approximately 1.585, and who spent the war teaching mathematics in Warsaw's underground university because the Nazis had shut down Polish higher education. When the Warsaw Uprising was crushed in 1944 and the Germans systematically destroyed the city block by block, Sierpinski watched his personal library and nearly all 32 volumes of Fundamenta Mathematica, the journal he had co-founded and edited for decades, turned to ash. He had spent years under occupation, writing papers and smuggling them to colleagues in Italy, inscribing beneath each one a coded note that Poland would survive. It did. His library did not. And Mandelbrot, who never stopped fighting, wandering between institutions for decades while the guardians of mathematical orthodoxy told him his pictures were pretty, but not real mathematics. The establishment was defending a 2,000-year lie. Euclidean geometry describes nothing in the natural world. Not a coastline, not a cloud, not a mountain, not a tree, not a blood vessel, not a snowflake, not a galaxy, not the path of a single particle. Every sphere in a physics textbook is an approximation. Every smooth curve in an engineering diagram is a convenient fiction. Every time a teacher draws a straight line on a blackboard and tells a student it represents something real, they are lying. Not intentionally. They do not know they are lying. That is what makes it worse. The false picture is so deeply embedded in how we teach and think about the physical world that we mistake it for truth. We built our entire civilization on a geometry that was never once correct about the shape of a single object. In the physical universe, we sent rockets to the moon using Euclidean approximations, and we landed, and we concluded the geometry must be right. But it was never right. It was just close enough for engineering purposes. Close enough is not the same as true. And the true geometry, the one that matches what reality actually looks like, was discovered over 100 years ago and is still not taught in most schools. The real geometry was there the whole time, in the functions they called plagues, in the sets they called pathological, in the curves they called monsters. And for 100 years, the people whose job it was to understand mathematics looked at the most accurate description of nature ever produced and called it an aberration. Stefan Banach proved in 1931 that most continuous functions are nowhere differentiable. The smooth functions, the ones Hermite and Poincaré and the Bourbaki school championed, are the rare exception. The monsters are the generic case. The monsters are reality. They always were. And what that reality tells you, if you follow it all the way to the end, is that infinite complexity is the default output of simple rules iterated, not the exception, the default. Stefan Banach proved in 1931 that most continuous functions are nowhere differentiable. The smooth functions, the ones Hermite and Poincaré and the Bourbaki school fought to defend, are the rare exception. They are a set of measure zero, meaning if you chose a continuous function at random from the space of all possible continuous functions, the probability of choosing a smooth one is exactly zero. The monsters are not the exception. The monsters are everything. The smooth, differentiable, Euclidean world that we taught ourselves to see is a comforting fiction projected onto a reality that was never smooth, anywhere, at any scale. And the roughness is not disorder. It is the deepest order there is. It is the signature of a process that generates everything from almost nothing. 5 symbols, 1 operation, iterated forever. And you are inside the iteration. You are not observing fractals from the outside, admiring their beauty, studying their mathematics at a safe distance. You are a pattern generated by a process you cannot see. Your lungs are fractal. Your blood vessels are fractal. Your heartbeat is fractal. The neural branching in your brain The very structure that allows you to contemplate this sentence is fractal. The quantum paths of every particle in every neuron are fractal. You are roughness contemplating roughness. You experience the output as trees and rivers and thoughts and galaxies and the sound of your own breathing. You call it reality. But reality may be nothing more than the boundary of something like the Mandelbrot set, being computed one iteration at a time, by a rule simple enough to write on a napkin and deep enough in its implications that no being inside the computation could ever exhaust it. You can zoom forever and never reach the end. You can study the pattern your entire life and never see the rule that generates you. And the fact that this is not front-page news, that you can walk into any school in any country and find children being taught that the world is made of circles and squares and smooth continuous curves, is perhaps the most successful act of collective denial in the history of the human species. Mandelbrot spent his life arguing that roughness was not ugliness, that the jagged, irregular, broken shapes of the natural world followed a deeper order than any smooth curve Euclid ever drew. The mathematical establishment spent a century calling those shapes monsters. Nature spent 14 billion years proving that the monsters were the only honest geometry there is. The equation is still iterating. You are still inside it, and there is no view from outside.